All right, so let's start with these examples. All right, so we did last time about the thermal expansion. So let's apply that, all right, and see how it goes, okay? So you have a poorly designed electric device, has two bolts attached to different parts of the device that almost touch each other in its interior, all right? So as the figure shows right there, they are almost touched. They are separated by 5 micron at 27 degrees Celsius. So the question is, at what temperature will the bolts touch? So, all right, so that's the whole thing that we would like to calculate, all right? Because now when you look at this one, each bolt it's attached to some sort of like there's a wall or something that sort of like put this bolt in place. So when the temperature rises, there will be an extension, right? There's some expansion going on due to the increase in temperature. But then, of course, because one side of this one already sort of like fixed in location, so you can expect that the expansion will happen only in one side. So if you look at the steel over here, once it gets hotter, it will extend out to the right. So assume that there will be some increase in length due to this portion of the bolt here, the steel. So let me put the ST there for that. So there will be a length expansion from the steel. Plus, you'll get some expansion from the brass. So let me call this portion delta L with the subscript B. Sounds good? All right, so there'll be a little bit of extension here. There'll be a little bit of extension there. And then you will see that these two bolts will touch when these gaps is closed. So that's easy to write out. The condition is just the delta L from the steel plus the delta L from the brass eventually will be exactly equal to the gap size, which is 5 micron. When you have micron, then you say it's 10 to the negative 6 meter. Sounds good? All right. And once you set this thing up, then it seems to be already a bit okay now, because if you assume that the temperature that they will eventually touch happens at somewhere, let's say X degrees Celsius. So you can calculate the change in the length of the steel bolts by using that expansion equation. So you say it's going to be the alpha of the steel, which you can look it up, and then times the original length of that brass piece, which is 0.01 meter. Okay, so that's good. So you can put 0.01 meter there. All right, I work everything under SI system. And then the delta T, the temperature change. So because we're going to start everything from 27 and then eventually it's going to get raised to X Celsius. So the change in temperature is going to be X minus 27. Sounds good? All right. And then you do the same thing with brass. So the brass will expand as well with its own coefficient of expansion. So let me put that alpha of brass there. All right. And the initial length that you started out with is 0.03. Very good. So far, so good. And it's going through the same temperature change. So it go from 27 to X. So the change is X minus 27. And that is it. So you equate everything to 5 times 10 to the negative 6 meter. And that's it. You can solve for X. And you are done. Okay, looks good.
Okay.
All right. Okay, so the reason I like this problem is because, all right, it's straightforward enough for you to apply expansion equations or relationships, all those stuff. Plus, it's just a little bit of like, setup of the initial equation for you to solve to get to the final answer. And then you will see that this is going to give you an idea what kind of like the difficulty levels of the question that will show up in the exam. Okay, so it's not too bad, right? So at around this level, I think this is good. Okay, cool. All right, so that's it, guys. So it's easy to use. Is a sort of like everything is under a linear relationship. So everything is still just like, addition, subtraction, multiplying numbers. So there are not a lot of mathematical operations involved here. Sounds cool? All right, so that's it, guys. That's done. Now, the topics that we are going to cover next, all right, before we move on to talk about heat and all the stuff that's it's like the main role or the main characters that we are about to talk. I'm just gonna squeeze in a little bit of stuff that eventually we're gonna use this one a lot, and it's about the kind of substance or state of the substance that we are eventually going to use in principle, or I mean mainly for our study of thermodynamics. All right. So before we get to that, everyone knows there are three states of matter, right? So you have solid, you have liquid, and you have gas. Okay. And for the solid, you guys know like the shape of it is pretty much fixed. And if you look deeply in the microscopic level, you assume that the position of those atoms or molecule that build up the solid is kind of like fixed in position. Even though you allow a little bit of like, oscillation, the wiggling and everything, but at least on average, the position of those atoms or molecules are fixed in place. Now look toward the other end for the gas. You don't have any fixed position for those atoms or molecules. So those elements can just move around crazily and everything, so they can just fill up the whole container. They can fill up the whole space. You guys know that if you let gas go, it will just spread out for the whole volume of the room, for example. So in that case, you have a gas phase. And of course, occasionally they can collide with each other and that's bounce each other, but they are not sort of like fixed in place. Okay. And then oh, that's a question. Okay, I'll answer that. And somewhere in between, of course, you have liquids, which is sort of somewhere in between. You have, right, well, not totally fixed in position, but I mean, it cannot just go all the way crazy. And then you just sort of like have the shape change depends on the container. So those are the liquids. All right. So that's one of your comments saying that what about plasma phase of plasma state of matter? All right. We can pretty much sort of let that one go for now because in the plasma state, that is the state that you have to really have to put some sort of like a super special conditions on the matters. And mainly most of the time you have to put it in a high temperature. All right, until they pretty much like split in some ions. So you have like positive portion of your atoms or molecule sort of like, split out from the whole structure, and there's another part negative. So it's more like you have some electricity and magnetism stuff that need to involve in the theory that to explain how plasma will behave. So yeah, even though they said that the plasma state is the fourth one, but I think just for our everyday experience, I think these three states are the main stuff that can explain what is going on with the matters. All right, sounds okay? All right, plasma is kind of nice and neat, but you need electrodynamics to understand its behavior. So I think we're gonna park that there. Okay, but that's good comments, guys, because I think it's been, I don't know, like maybe half a century already that they sort of define the fourth state of matters to be a plasma, right? But that's that's what it is. All right. Okay. All right. So why I would like to why do we have to talk about the states of matter? The reason is this: what we are interested in the most is going to be gas. Why gas? The reason is because eventually we would like to have a system that can perform many things and allow you to be able to study those changes. So you want a lot of actions going on for you to be able to study thermodynamics of a system. So that means if you use solid system, then the bad thing is the solid doesn't change its shape so much. So it means you're going to lose the action of expansion, contraction. I mean, you don't have any things that can going on much. So studying thermodynamics in a solid state, it seems like it's going to be like, not very dramatic in terms of the change, right? If you want to stick with the liquid, it's still tough because liquid are so depending on the conditions, depend the type of liquids. There are no grand, pretty much like grand equation or grand relationship that can pretty much explain all kinds of liquids. There's so many variations. But then when you look at gas, the system is simple enough that when you look individually, it's just like atoms or molecules and stuff. Like it's okay, it's like a single unit of stuff. And then because they are so far apart, we can assume something simple to this. For example, let's say there's no interaction between them. All right, so that's make things a lot easier. With respect to liquid and solid, that you can see that there will be tons of interaction going on among their neighboring atoms. Okay, so these are a lot of stuff going on. And if you have to take care of those interactions, then your job will be already hard. in the first place. But when you look at gas, all right, if you cut off all the interaction among their neighboring atoms, just forget about it. All right, your system is going to be simple. Plus, in the gas system, you allow this gas to be able to, I mean, because gas fill up the whole volume of the container anyway. So that means these allow you to be able to adjust the volume. You can have some action going on that you can sort of trace and study. And all right, I'm going to take a look at some property of this gas and see how would that relate to the thermodynamical changes. All right, so this is the reason why when you first studying thermodynamics, gas is going to be your initial system for your study. All right, does that give you like sort of good motivation here? Because the reason I have to say something about this is because every time you talk about thermodynamics, people always say that thermodynamics works everywhere. I mean, everything is governed by thermodynamics. But then when you study it, it's like, oh, John, why do we only talk about gas? When we talk about like gaseous system, this is the reason, right? It's easy to use in terms of like, okay, it can, showcase so many things of thermodynamics until you understand all aspects of thermodynamics. And once you understand everything, then you use thermodynamics laws and everything to apply to some other things. Okay, so that's the whole idea. All right, so when I said we want to make things simple as a starting point, and we get rid of those interaction between those atoms that made up the gas, then we say we are building something sort of in our head. So it's sort of like a theoretical system, or I mean, sort of like thought system. That's why we would like to build a ideal gas. Is the gas in your ideal situation, okay? Because the real gas is complicated. So forget about liquids, forget about solid, that will need some other theory to help. But if we can reduce every gas is down to just an ideal gas, things is going to be super simple. First, we don't care about the interaction between them. So we assume the ideal gas does not have any intermolecular forces or intermolecular interaction. So that's good. So we get rid of those. All right. Don't care about the interactions between molecules. Plus, I mean, in reality, these approximations can be done. I mean, you can make your gaseous system approaches ideal gas scenario when you lower down your pressure, make the pressure kind of low, and then you sort of like raising the temperature a little bit higher. So all the gas move quickly enough and stay far apart enough. So the properties of those gas is approaching ideal gas. Does that sound good? All right. So you try to minimize the interactions, and then you try to pretty much make them move quickly enough until like, okay, the interaction, it doesn't seem to have any effects on those gases. All right. Something like that. Okay. However, because we still allow these molecules or atoms to collide among each other, so that's no big deal. Collision is fine. As long as you assume that collision is an elastic collision. So it doesn't take away any energy or you lose any energy during the collision. So this is perfect. All right. So that is the definition of an ideal gas. So it's the gas that allow you to sort of like treat them ideally, no interactions. Okay. Every collisions are elastic. Perfect. All right. Why do we need this? The reason is because, as I said last time, thermodynamics is trying to explain a system without using microscopic parameters. You guys with me? We don't want to deal with the microscopic parameters. What are those? Let me give you an example. All right. So you remember last course 101, when you did fluid, you talk about pressure on a wall, for example. You are able to calculate pressure. And then you say the pressure is force per unit area. And then you talk about the force that fall perpendicularly on that surface, right? And that's what it is. This force is kind of tough for you to actually measure because all the forces come from what? Come from the atoms of the gas knocking on the wall and bounce back, right? Remember this one? Yeah. So you have like, million of these molecules hitting the wall one by one, and everyone changing the momentum, leaving some impulse and create some forces on the wall. But then you said, oh, Ajahn, I'm not going to be able to track all those forces due to each collision of those gaseous molecules. Then what you want, well, Ajahn, just measure the pressure and be done with. You see what I'm saying here? All right. So the pressure is that parameter that is in the level of the macroscopic, the big picture. Okay. So the pressure is the parameter that you can measure without carrying the detail. You don't have to worry about the fine detail of what is going on in the microscopic level. Does that sound reasonable? All right. So that's why the pressure will be the one that we will use to describe the state of the system. In our case, the ideal gas. And we're going to call these parameters to be your state variables, because these are the things that you can vary in value. You can change the pressure, you know, on and on. And each pressure will eventually be able to identify the state of the gas system. Sounds good? Okay. Any other things that you can sort of deal with this? Well, of course, we studied about this last time. Remember, we talked about temperature on Thursday. And the temperature is already give you the information of the total kinetic energy on average in your system. See? So this is a good thing that you don't need to do that 1/2 mv square and then you do the average. No, you say, I don't have to do that. All I need to know is just come into the room, take the temperature, and then that temperature will already lead you back to what should be the average value of all those crazy molecules running around. What are those kinetic energy and all this stuff? Does that make sense? All right. So the temperature will be another state variable. So I hope by this time you already see what thermodynamics is trying to get to. It means you're trying to describe a system using macroscopic variables and allow you to be able to identify some states, some changes or whatever. And then eventually we're going to connect to the laws of thermodynamics this way. Okay. And the reason that we are focusing on ideal gas, it's because, yeah, we have tons of variable that eventually you have a known relationship between them. So that make it easy for you to be able to identify the state of an ideal gas. Does that sound reasonable here? Okay. Pressure is good. All right. So we just talked about that. Temperature is nice. Another macroscopic parameter that you can do easily is just measure the volume. And now when I hit these 3 parameters or variables, now you start sort of, you know, remind you something, right? Think so? Yeah. Maybe not. Anyway, so that it's just like, okay, it's kind of like vaguely remember that we saw this kind of thing before: the pressure, the temperature, the volume. And then if I throw in this number of molecules, well, okay, that's something that's, well, but I thought number of molecules are sort of like microscopic because you have to count like 1, 2, 3, 4, 5, 6, 7, right? But then we say, hey, Ajahn, we talked about the Avogadro number. So there is a 6.02 times 10 to the 23. That is a Avogadro number. So if you take this one to be, all right, we assume that this is a big number, but we don't want to deal with the micro stuff. Let me name this one 1 mole. With me? All right. So you have a unit of mole. So it's like, okay, so this is like a big unit over here that you can use. So instead of doing detailed stuff, 10 to the negative 3, you wrap them up and call it a 1 mole. So we have the small n for that. So if you have the number of moles of gas, if you have 1 mole, it's equivalent to having 6.02 times 10 to the 23rd numbers of molecules or atoms inside that gas. Okay, that's that familiar? Yeah, is it familiar to you guys with this one? All right, so we use capital N for the number of molecules or atoms. We use small n for the number of moles. So the conversion between the capital N and small n is easy. If you want to take the number of mole out of your gaseous system there, you just take the total number of atoms or molecules and then divide it by Avogadro number. That's an easy relationship between capital N and the small n. All right, cool.
Okay.
And that is done. So combining this, now we have more stuff. You can pick the capital N or small n, on and on. Sometimes in some textbook, you might still want to go back to mass. But I mean, for us, for our purpose, I mean, we can go back to calculating the mass of gas very easily. But I don't think we use much of the mass of the gas because usually we don't weigh the weight of the gas. Does that make sense? You don't put gas in like a scale or something and weigh them. So usually it won't happen much. So that's why we will stick with the number of moles, or you can convert them to the number of molecules. All right. And then if for whatever reason you really want to calculate the mass, then all you need to do is just figure out what type of gas you're talking about, and then one molecules of that gas will has what mass, and then you just multiply it back. Okay, so for our lecture, we'll stick with the small n and the capital N. Sounds good? All right.
Okay.
So with that in mind, you have now, all right, already sort of like have seen this a couple of times, the Avogadro number. And this is just a constant that you can always refer to. Avogadro number is always a fixed number right here. But we have a couple more of the constant that you can combine, but those constants shows up in this relationship right here, guys. And that is the equation that you probably familiar with. Yeah? Sounds good. So this one is the one that you might have seen from chemistry or in high school physics before, is PV equal to nRT. So this is a nice thing about studying a gaseous system. If that gas is an ideal gas, it will always follow PV equal to nRT. But of course, because we are looking at like an ideal gas and it's like simple enough, and we want to make things super simple. So this one is for monatomic. So that means for now, we're going to focus on this one, just to be clear. All right. The reason that we want to focus on this one, because later on, we will have to calculate some other stuff too. All right. So we'll still assume that if it's monotonic, other relationship will have a particular shape. But anyway, as long as it's an ideal gas, even though it's non-monatomic in this case, it's still PV equal to nRT anyway. Does that sound okay? All right. But anyway, we're going to maybe just focus or confine ourselves with the monatomic gas most of the time. All right. Okay. So when you have an ideal gas, it will always follow this equation. You can call this equation the equation of states. Why this is the equation of states? Because once you pick P, the pressure of the gas, you know the V, the volume of the gas. If somehow you know the number of mole, you can use this equation to figure out the temperature right away. Does that sound good? All right. So that means ideal gas always follow this equation. So this, you can take this one as like a law. Like it has to be. It's not an approximation. It's not. It has to follow this one. PV equal to nRT for an ideal gas, of course. Okay. And somehow, if you don't want to deal with the small n, you can convert this to a capital N. So what you can do is you can turn this small n into a capital N by saying that it's just the capital N divided by Avogadro number. But then what pops up right here is another constant that you squeeze in here, the R. All right. And that is named gas constant or universal gas constant. So it has a particular value of this one right here, about 8.31 joule per mole Kelvin. Okay, cool. All right. And once again, if you convert this into capital N, so as you can see, the R is already a constant. The Avogadro number is also a constant. So that means the ratio between that capital R and the N sub A, that Avogadro number, will give you another constant. And that has an extra name as well. We write it as K sub B, and that is a Boltzmann constant down here. All right. And it has a fixed value as well, around here, 1.38 times 10 to the negative 3 joule per Kelvin. Cool. All right. So that's the nice thing about this gaseous system that we are about to study. It always follows this gas equation or the equation of states. PV equal to nRT, or PV equal to capital NKT. Okay. And now this is one example that I discussed last time. This is a pure equation that you don't just only look at the change in temperature. You want value of the temperature. So the temperature in this equation has to be in an absolute scale all the time now. So you cannot plug in the temperature in Celsius, in Fahrenheit, or whatever scale. It has to be an absolute scale in here. Okay. And the nice thing about this one that you probably have seen before, if you have seen one in chemistry, is because you have PV is always equal to nRT. So somehow, if I move things around a little bit, so let me write it like this. Here we go. So let's say you have a gaseous system and your system doesn't have any leaks. You are not putting more gas into the tank or in your container. So the amount of gas that you are dealing with is fixed. So N is fixed. You can talk about N or capital N, doesn't matter. They are the same thing. And of course, R is constant. So that means what you're doing is you just make the right side of this equation to be a constant. And that, of course, the left-hand side of this equation will stay fixed as well. Then that's allow you to be able to compare between two conditions of the gas. You guys with me? So that means no matter what you change the state variables of the gas, the ratio of PV over T stay fixed all the time. And this is the reason why you might have seen this kind of things before. You can always compare two states of a gas by saying that the PV over T stay constant. And sometimes you see something like this. P1, V1 over T1 equal to P2, V2 over T2. All right, it's kind of like, if you want to memorize this, it's kind of a boring relationship, but now we understand this one because, of course, it's just the right side of this one is just number of mole multiplied by a constant. Okay, cool. All right, so that's the things that we are eventually going to utilize a lot, and eventually we're going to focus on the gas system for our thermodynamic study in the near future. Sounds good? All right, so this one is like sort of like a squeeze in here just so you have a quick connection talking about the state of matters. All right, but for now, we will just sort of like, okay, do like a quick check of what kind of things can be done with this equation of state. Yeah. So for this example right here, all right, so you guys, my voice and the slide and everything looks clear and good. I don't know, to me, there's some lag going on with the visualization somehow. I don't know why. It happens from time to time. My new laptop doesn't seem to respond well anymore. Okay, but to you guys, everything's still looking good. All right. Okay, just let me know if there are any technical difficulties. All right, just you can just put in the chat box if you want. Okay, try this one, guys. An ideal gas occupies a volume of 100 cubic centimeter at 20 degrees Celsius. Pressure is given. What is that? 1, 2, 3, 4, 5. Is that 6? Is that 5 or 6? 1, 2, 3, 4, 5. 10 to the 5th. Let me write it like that. Pascal. So good. Pascal is in the units that we like in the SI system. Okay. Determine the number of moles. All right. So you want the number of moles. So that's mean you would like to figure out the small n. Okay. Also find the total number of molecules. So if you want this one, that's your capital N. All right. So from the look of this one, it's not bad, Ajahn. Let's attack this. So start with P, V equal to small n RT. That's easy to do. So the number of mole will be easy, but the only annoyance in this problem is the unit conversion. We want them to be sort of like, you know, follow the same units over here. So let's start with the pressure, shall we? The pressure is already good because it's already in Pascal system. So you can substitute this one to be 10 to the 5th Pascal. So that's fine. This one is good. Next, what about the volume? Here we go. The volume right here, it's in cubic centimeter. That's not good. You want them to be in cubic meter, right? So I can convert that. And everyone knows centi is 10 to the negative 2. All right. So here, I think this is a good chance for me to speak about the unit conversion. So I don't know what have you done before in the past. All right. But the way that I treat those prefixes, like come up and then you want to change, convert the units from small to big, big to small, whatever it is. What I'm doing this is this. I treat C as a number. I think everyone knows already C is 10 to the negative 2, correct? So every time that I see centimeter, to me, it looks exactly like two numbers multiplying. It's like this. Same thing, no difference. Does that make sense? Okay. So if I have centimeter, it's 10 to the negative 2 multiplied by meter. So if I want cubic centimeter, so what I'm doing over here is this cubic centimeter. So it's the same thing as I take these numbers and just do the cubed function. So that will be exactly equal to, or I'll just do simple sort of exponential calculation over here. So it's going to be 10 to the negative 6 and cubic meter. You guys with me? All right. So I just treat those prefixes just like a number. So what I can do over here, I can just say, okay, I'm going to get 10 to the negative 6 in the front. And if I pull this one out, whatever left here is going to be in cubic meter. And I'm done.
Okay.
Okay. I don't know if you like this or not, but if you like it, you can take this one along with you. That's kind of good. All right. So that's what it is. All right. And the good thing about this one is that allow you to convert units back and forth really easily. For example, if I have, let me just, do a simple one. Let's say if I have 1 cubic meter, but then somebody just come in and about, hey, give me cubic micrometer. I don't know, is that how to pronounce it or not? So it's a micrometer cubed. That's what you want, right? So I say, I don't know what it is, but I want the units of like a cubic micrometer. Just convert them to me. So what you can do is you just take a look at this. Is 1. You have meter cube here, right? So let me write here, meter cube. What you can do is you just multiply by the mu and divide it out the mu inside that cubic function. You guys with me? All right, because I treat this prefix, the micro, the mu, as just a number. So what I'm doing is just multiply by 1, mu over mu. But then I'm just going to keep that micrometer here together. That will be my final unit that I want to keep. So at the end, what I'm getting is going to be 1 divided by mu cubed, and it's in a unit of micrometer cube, something like this. All right. So that's allow me to manipulate the unit up or down or whatever just by treating this as a number. Does that sound reasonable enough? Okay. All right. There's a question coming. Is meter just 10 to the negative 10 to? Yeah, that's right. Oh, no. Wait. Just 1 meter. Oh, wait. 1 meter? 1 meter is 1. So it's 10 to the 0, I think. Meter is just 10 to the 0. That's the first one. Yeah. Does that make sense? Because 1 meter is already 1. So it's, you can call it 1 is 10 to the 0. And then I think that is what is the deca? Is that deca 10? I don't know. Deci is 10 to the negative 1, on and on. There are special name for that 10 to the 1. It's, I think, a decameter. Something. For sure. All right. So that's how you can manipulate your units, all right, by treating all those prefixes as just you treating a number under product. Okay, you just do simple multiplication, on and on. Okay. All right. Come back here. All right. So equate that. Small n, that's what you want to figure out. The r, just keep it as r. You can always substitute an actual value of r later. And the t, look at the t here. Now here we go. It's the 20 degrees Celsius. That's not allowed in this equation. This equation needs an absolute temperature scale. So that means you have to convert this one by using that constant 273. You can do 0.15 if you want, but I think 273, I think this is already good for us. Plus 20. That's already turned this Celsius into Kelvin scale. And that's it, guys. From here, you will be able to calculate what should be the number of mole. Done. All right. And of course, if you like to figure out the capital N, everything just go exactly just like what we just did over here, except you just use capital N and pair this one with Boltzmann constant instead. But everything else look exactly the same. This will give you the capital N. And you are done.
Okay.
Okay, cool. Not too bad. Right? But I mean, the purpose of this one, I would say mainly is talking about the unit conversion. Okay, so this one is just, I hope if you like these techniques, I think that's And that if that's good, then you can just grab and just apply it later. Right? But if you don't like, that's fine. I mean, I think everyone has their own ways of treating, units conversion, like, that's different approaches. Okay, any questions so far? So far so good, not too bad. All right, it's kind of like easy Saturday. Yeah. Okay, that's doable. All right, guys, try this one. All right, so this one is going to be a straightforward one, and it's showcase what is going on when you are changing the state of a gas. You have a pure helium gas is admitted into a tank containing a movable piston. Here you go. So now when you have a movable piston, it means now the volume of the gas can be adjusted. The initial volume, pressure, and temperature of the gas are given. All right, so that's good. Units looks good. Cubic meter, kilopascal, that's fine. Kelvin, that's nice. If the volume is decreased to a new value and the pressure is increased to another value, what is going to be your final temperature? See? So this is what happened because we treat our helium gas to be an ideal gas. So that means the PV equals to nRT is valid. So when that equation is valid, you can compare two states of gas by saying that P1 V1 over T1 is equal to P2 V2 over T2, Okay. All right. It's kind of like just teasing these equations in a boring way of memorizing this thing. Okay. So what we can do is just plug in the value and see how it goes. The pressure, that's nice. Initial pressure is 200 kilopascal. But the nice thing about this one is because you only need to compare between left and right. So that means you don't have to even convert kilo to just a regular Pascal. If you use kilopascal on both left and right side of the equation, then you're good to go. Okay, you guys with me? Yeah. So I'm not gonna have to do any units conversion here. I'm just gonna do it. Just leave it there. Kilopascal. That's fine. What about the volume? That's fine. Volume is 15 times 10 to the negative 3 cubic meter. That's good. Okay. What about the temperature? The temperature is 300 K. Is in a Kelvin scale already. That's perfect. That's done on the left-hand side. That is your initial state of this gas. Now you equate this with the right side of the equation. Do you know the new pressure? Yeah, we know that. So this is 350 and it's kilopascal. Perfect, right? So this eventually is going to cancel in terms of the units. Units are coincide, so everything is good. Now followed by the volume, right? The volume is also given right there in cubic meter. You just put it there. That is fine. And that's it, guys. You can figure out what should be the new temperature there, and you should be done right there. Cool. Okay. All right, simple enough between these two. All right, so we're gonna have a lot more fun with the equation of states of an ideal gas when we really deal with the thermodynamics next week. All right, but at least this give you sort of like an introduction, or at least like refresh your memory a little bit about the equation of states. All right, and what are the variables that you are eventually going to need. As you can see, we throw away forces, we throw away velocity, we throw away like acceleration, we don't want momentum, we don't want anything anymore, right? Those considered to be a microscopic parameters in the context of thermodynamics. Cool. Alrighty, keep going. All right, so before the break, I would like to talk a little bit about heat. All right, give you some sort of something to think about during the break. I don't know if you care about this or not, but anyway, so we are going to talk about heat a little bit, and I'll just throw out one big question: what is heat? All right, and I know you guys don't like this kind of question because it's just all right, Dan. It's like you can answer whatever aspect you want about heat. So instead of just talking about the definition of heat on and on, let me ask you one sort of like my favorite question here. What kind of feeling that you feel right now when you see this word? Here we go. I love to show you something that's kind of like that's not so good, but it's kind of like weird. How do you feel about this word? Heat energy is like, I'm just compound the heat and the energy together. So this one is kind of annoying a little bit for those that try to translate this one in Thai. There was a little bit of, I would say it's not a flaw, but it's sort of like a convenient way of translating this. And it's translated nicely to พลังงานความร้อน. So that's sort of like, all right. The reason for that is because in Thai, we can sort of translate heat means ความร้อน. But let's speak in terms of what does it mean by heat energy? What do you think? The answer is, well, actually, this one is an illegal term. And of course, it looks weird, all right? For some of you, probably like, it doesn't sound right. It doesn't make any sense. But for those of you that feel like that's okay, there is something technically wrong with this word. When I say technically wrong, because this is not good. The reason this is not good, because for this to be correctly mentioned about พลังงานความร้อน you need to use the thermal energy, right? Okay, so this one is fine. Thermal is sort of like, okay, this is a better. You have an adjective that allow you to modify the word energy and say, this is the energy that related to something thermal, something about temperature, something on and on. All right. And in Thai, you can still translate this one as a พลังงานความร้อน anyway. Okay. But anyway, to be sort of like strictly correct, probably it means พลังงานเชิงความร้อน. Every time you have an adjective, you put like คำว่าเชิง on it. But anyway, come back to us here. Oh, there's a question here. I heard it's the dissipated energy when I learned about the energy topic last trimester. Very good. All right, so that's exactly what we want. It turns out the reason we need the word thermal energy to talk about the energy of a body, okay, that's related to thermal stuff, then you can call those energy of that body to be thermal energy. Just like 1/2 mv squared is going to be kinetic energy of that body. Maybe mgh, the gravitational potential energy of that body. You can put like some value to it, and then you can say, hey, that is your thermal energy of that body. That is fine. But for the word heat, turns out the meaning of the heat is energy transfer. You guys with me here? All right. Okay. The key point to take here is there is some sort of like a dynamics going on right here. It's the heat transfer. You need the transfer thing for the heat. So that's why we cannot use heat energy, because it's the energy of the energy transfer. That doesn't make sense. Right? When you say heat energy, it means the transfer of the energy requires some energy. So it's sort of like redundant, or it's even like illegal, or it's wrong. That's not good. So all you need is just heat by itself. It already means some energy is transferred. So what you said over here, that's already correct. It's some sort of like dissipated energy coming out, coming in. The reason that you need the word dissipate, because that is an indicator of something is moving. There is some transferring. There is transaction going on. Okay, cool. All right, so that's why heat is not an energy that is contained inside a body. We cannot. If you would like to mention about the energy that contains inside a body, you have to use thermal energy of that body. Okay, that's that good. So what I'm trying to talk about here is just so for you to be able to see the contrast between heat and energy. Energy is something contained inside a body. Heat is the transfer. This situation sort of sound familiar to you? What do you think? Maybe. Energy is something that's contained in the body. Heat is the transfer of that energy. You have done this before in 101. Remember W equal to F dot delta S here. Yeah, sounds reasonable. Sound like okay, back in the day, what you had this one done to a body, for example, you apply some force, and then this thing translates by some displacement, on and on. What you did to this is you do perform work on this body. You might have like an object of mass M or whatever, But what it does is like when you apply the force, push this box or push this body, slide along the horizontal surface by a distance delta s, on and on, you performing a work of F dot delta s, right? This is good. But what it does is it's transfer the energy of whoever performing this push. It can be me pushing this. So it's transfer energy from me to the body, to the box or whatever this box right here. So the box at first, maybe it's starting from, stable, no movement, nothing, it's just standing still. But once I push it, it translates. So it's starting to move. So when it moves, it contains the kinetic energy. So what I did was just like the pushing transfer the energy from my body. Maybe I just had breakfast, I burn everything, I flex my muscle, push whatever, and then I transfer the energy of mine to the kinetic energy of that box. See, all right. So that means what I'm trying to say is we have already done this kind of thing. Work is equal to what? Remember? Change of the energy. That's what you did before. That's the work energy theorem. And you have conservation of energy. Everything has to be conserved and everything. And then you say, okay, the work done by the external force is going to be equal to the change of the energy of that body. The situation is exactly the same here. But is the exchange of the energy not by the mechanical stuff anymore, but you do it through thermal effects. So this is back to the example that we did before. So now to be able to have a complete picture of everything, I have to tell like, hey, my body temperature is 37 degrees Celsius and the temperature of the box maybe at 25 degrees Celsius. So not only I'm pushing the box, not only I'm transferring the energy through the mechanical process, actually I am transferring heat from my hand to the box as well. I mean, if my hand is warm, I touch the box as it's cold. So there will be some energy leaving my body to the box through that temperature difference. You guys with me now?
Okay.
Okay. So that's pretty much give you the compare and contrast between what you did back in the day of the pure mechanical system. And here you have additional stuff, which is thermal effect. And that's where the thermodynamic is. Cool? I don't know, is it cool or not, but it's just like, okay, done. All right. I hope you get my point here. Okay, so instead of keep talking about, all right, because the gas probably not gonna have like, okay, total kinetic energy average. You're not gonna like, keep saying this all the time. Like, okay, it's the average of the kinetic energy of the molecules in the box, on and on. You have to do statistics. You can just wrap them and call the energy of that system by saying that it has the internal energy. Okay, cool. All right. So the role of the internal energy, it is exactly the role of the energy that you calculate before. Okay. Back in the day, you have 1/2 mv squared, you have mgh, you have 1/2 kx squared, you have so many forms of energy. But for our thermodynamics business here, we're just gonna call them internal energy. And because what we are dealing with over here is gonna be some simple system of an ideal gas, so that's something that can be calculated. Okay, that you're going to see this next week. But at least at this point, you should see the things that we are trying to get to, I hope. All right, sounds good enough introduction to you guys, I hope. All right, so if this is the case, all right, so let's take a look at the units of this one a little bit, because now we understand that this is just the energy transfer. So the units still the units of energy. So heat, it still has the unit of joule. However, because the study of this energy transfer dated back in history, like they're talking about the change of the temperature of water most of the time when they started the study of this heat business over here. So they do the experiments on water, and at the time they invented another unit, and that was calorie, and it's still being used until today. So I think this is a good thing that for you to be able to convert between the calorie unit and the joules, the SI system unit today. Okay, so what it is 1 calorie is 4.2 joules. Okay, so this is a conversion factor that you can always use to to convert between them. Okay, and all right, because we talk about the calorie, okay, then I think we're gonna close the first half of the lecture by just like, if you sort of like recognize this is a nutrition fact, the label that's stuck on the food packaging and everything. All right, so you probably see this already, like, okay, if you eat this stuff, then it will provide you with the 230 calories. This one is different. It's a big C calories here. This one is called food calorie. All right, so just so you know, this is like FYI. So the food business, they claim the capital C calorie to be 1,000 calorie of us. Okay, so every time you look at the food packaging, that calories that you see, you have to multiply by 1,000 to get back to the calories that we use in whatever physics here. All right, but for European nutrition information is a little bit better. They provide you with both systems, so that's kind of nice. You don't have to do the conversion yourself. They already sort of give you both in kilojoules and kilocalorie. So they don't even have to quote like capital C or anything. They just put right out, like it's in SI system and in the caloric system. So that's kind of nice. Okay, cool. All right, guys. So let's take a break right here. All right. And after coming back, then we're going to take the business of heat a little bit further, and then we'll be able to do some calculation with this. All right. So let's take 10 minutes break right here. All right. I hope I did a little bit too long, maybe. Sorry. Yeah. All right. So what can we do with this? All right. So, I mean, there's a little bit of a historical note about the calorie and joules units. Actually, it came from the day that actually physicists or scientists didn't know the equivalence between the mechanical energy and the thermal energy before. All right, until James Joule, Joules, the one who we use the unit honoring James Joule, that sort of like discovered this equivalence between the mechanical energy and the thermal energy. All right. So back in that experiment, I mean, sort of like the first day of the experiment, actually he did the experiment that trying to convert this, like the MGH. And every day now we kind of like, okay, John, no problem. We sort of like know this. This is nothing new. But back in the day, it was just sort of like try to make the connections between this. So they actually have like a not super, but like heavy masses hanging above the ground, and they just sort of like let it fall down to the floor, and it attached this to a paddle that can just, you know, sort of like make the water move a little bit, and then measure the temperature change of the water. And it turns out they do the experiment and showing that the amount of energy that's supplied to the water, turns out that the water temperature will increase according to the relationship between, just like you have the energy from gravity move to the thermal energy of the water, something like that. All right, so that's kind of like back in the day, there was like already like a big accomplishment, but because right now it's already well established, what kind of energy means same thing. It's just energy. So they can convert, they can transfer it, they can change the form of the energy back and forth. No more big deal. All right. So that's sort of like the things that at least keep in mind that there's connection between mechanical and thermal energy at all the time. Okay. All right. So what we are trying to do today is a simple derivation of, once we understand heat is the energy transfer, but in the thermal aspect of the body. So what we have is we're going to learn something about the property of the matter called specific heat. All right, here we go. So that's what we're trying to do. We want to take a look at the specific heat. What does this mean? Think about this. So if you have an object, okay, and then somehow you supply the energy to it. So you move some energy to that. So we are going to use Q for that. So now you add some energy to the body, all right, or you can call this your system. So you transfer some energy to the system. So that is already your energy transfer. So assume that the transfer is due to, we would like to talk about the thermal aspect of this one. So the effect of this energy that get to the system is going to raise the temperature. the temperature will be higher. All right, for now. So what we have over here is, it means that the amount of temperature change should depend on the amount of energy that you supply to the system, correct? So that's sort of like, okay, Dan, that seems easy enough. So the temperature change should be proportional to the amount of energy transfer. All right, so I'm going to turn this proportional relationship into an equation. So I can turn this by having an extra constant in the front. Or you can imagine, like, Adan, the delta T will be big or will be small. Not only the Q will determine the change of the delta T, but you have to think of the object itself. Is the object has an ability to store that energy or not? So if the ability of this object to store an energy is small, so it means it doesn't have a lot of space for it to carry the energy, the delta T will be high. Does that make sense? Okay.
Okay.
All right. So on the other hand, right, if this object has like a huge capacity, it can store a lot of energy. So when you supply some energy to this system, then it will not change in temperature much. So I would like to make a quick analogy, like, for example, if like you're eating food, for example. So if your stomach is kind of small, only small amount of food will already make you feel full already. That's easy because your stomach is kind of small. But then if you have like a big stomach, for you to feel full, you need a lot of food transferred to your body. Does that make sense? All right. So that's why that C that introduced in here, that is your capacity. That's your stomach right there. But this is the capacity that allow you to store thermal energy. So that's why we call this heat capacity. All right. Looks good. Okay. So this is the capacity of this whole object to store thermal energy. Okay. So that's an easy expression here. So the amount of energy supply, Q, will be equal to the product between the heat capacity and the delta T, the change in temperature. However, this equation is kind of still hard to use. The reason is because if you have, for example, an object, like a small one, but then you have exact same substance, but a bigger one, let's say 4 times bigger. So I can sort of like draw this one. So everyone know if this one has like a specific heat of C naught, for example, this one should have 4 times that. Everyone kind of like know that, right? And if you bring like a bigger piece of this one, let's say now you have 9. So you should have known already that, hey, this piece of object should have like 9 times ability to store energy. So from the look of it, all of these made of the same material. Let's say, for example, this one could be like water. You bring in 1 kilogram of water. The next one, you bring 4 kilograms of water. Third one, you bring in the 9 kilograms of water, but they're all made of water. So why don't we just say, hey, what is the ability of water to store some energy? So what you do is okay, Dan, let's do per unit of water. All right. So let's do the capacity per 1 kilogram per kilogram. And later, if you bring in 4, you just multiply by 4. If you bring in 9, you multiply by 9. Does that make sense? All right. So that's why we defining specific heat. So it's the heat capacity per kilogram of that substance. So this one is going to be sort of like universal across the universe. You know that no matter where, when, how you talk about, as long as you are talking about water, every 1 kilogram of water will have this amount of heat capacity. Now that sounds good. Okay, so that's kind of nice. So it's more like you try to make like a universal properties of water, and this is one of them, the ability to store thermal energy, something like that. All right, so we name this specific heat. Okay, so the ability to store thermal energy per kilogram. And once we sort of define this one, you look at the table on the right, and as you can see, now we can define specific heats for aluminum. So now you know it's 900 joule per kilogram. So later on, if you want to bring in 10 kilogram of aluminum, you just multiply by 10. You get the heat capacity of that 10 kilogram aluminum. Okay, cool. So that's a simple relationship saying that, okay, the capital C, the heat capacity of that object, is going to be just purely the products between, right, how much you bring in, the mass of that substance, and then you multiply by the specific heat of that substance, and you're done. Cool. All right. And that's lead you to the equation that we're going to use most of the time. Heat transfer Q equal to MC delta T. Here we go.
Okay.
Right, so this one probably look familiar to you, but at least that's sort of like a recap of what you have done before. Okay, and this table on the right will list heat capacity of substances that may be useful later for you to be able to refer back to this table, grab the number and do the calculation. All right, so that's good. Q equal to MC delta T is kind of like, okay, it's still once again a linear equation, easy to use, no calculus, there's nothing there. That's kind of nice. Now, just to check your understanding, okay? So compare this. I have a scenario for you. Let's say sand versus water. When you go to the beach, any beach, right? When you go to a beach, the main two substances that you see in front of you is either the water in the sea or the sand on the beach. Does that make sense? Yeah. Let's say you go there during the daytime at noon. So water and sand receive the same amount of energy from the sun, let's say. Okay, so that's good. Everything seems to be in control. So the question is easy. You think sand or water has a higher specific heat? What do you think? All right, when I talk about specific heat, mean, of course, you compare like kilogram per kilogram, right? Think of it like if you have a 1 kilogram of seawater and 1 kilogram of sand. Yeah, so you compare the heat capacity between those two. What do you think, guys? Just getting a little bit of motivation there. Water, very good. Very good. All right. Any other comments here? Contribution to the class? Okay. Very good, guys. So the answer should be water. Why? Because you can feel by your feet that the sand is going to be a little bit hot to your feet, right? When you walk on the sand, as compared to when you walk into the water, it will be a little bit cooler there. So you can see that, of course, the higher value of the specific heat of water result in lower temperature change of the water. So the sand will have a higher temperature during the day than the water because the water has a higher specific heat than the sand. Okay, makes sense? Because Q equal to MC delta T. So it's a product between two terms, this term and that term. If the delta T is big, that means this one has to be small and vice versa. Okay, cool?
Okay.
So I hope you sort of get the sort of like the underlying, rule of thumb saying that you can pretty much tell about the heat capacity easily by checking the temperature change. Of course, in the control scenario over here, that's easy to compare. Okay. All right. Next, take a look at numerical calculations a little bit. So in the next example says the temperature of a silver bar rises by 10 degrees Celsius when it absorbs 1.24 kilojoule of heat. Now the mass of the bar is 525 grams. Determine the specific heat of silver. So this one is a straightforward plug and play kind of problem. So let's take a look at this. Q equal to MC delta T. Yeah, that's easy to use. The amount of heat is already given right here, 1.24 kilojoule. I can actually just plug it in right here. Kilo is 10 to the third joule. There. All right. Right-hand side, the mass of this one is in grams, so you can turn this into kilogram by divided by 1,000. That's good. All right. The C, that's what you want. Let me subscript this one as a silver. And then the delta T, because it rises by 10, yeah, you can put it here as 10. It doesn't matter if it's in Celsius or in Kelvin, the change of the temperature will be exactly the same in both scales. And that's it, you're done. You will be able to find your specific heat of silver here. All right, so this is easy plug and play, know your information and then apply this. Now, let's try a little bit more practical, or more connected to a real world scenario here. If you have a water heater that is operated by solar power, now if the solar collector has an area of 6 square meter and the intensity delivered by sunlight is 550 watt per square meter, so that's good. This is pretty much actual scenario here, people starting to install solar panel on their roof. How long does it take to increase the temperature of a cubic meter of water from 20 to 60 degrees Celsius, guys? What do you think? Okay, first of all, let's calculate how much energy we're receiving from the sun. So you have a panel of 6 square meters. So let me sort of like draw a diagram over here. Let's say you have a solar panel here and it has the area of 6 square meters. All right, the sun is sort of like shining over here. Now, even though you don't know the definition of the intensity, we'll have a chance to talk about the definition of intensity later when we talk about waves and sound and light and everything. But for now, you should be able to extract the information by looking at the unit. Look at the unit is watt per square meter. So that means each square meter of the panel, you can collect 550 watts of power. All right. You remember the units of power is watt. So that's good. So that means that the total power that this panel can generate by absorbing the energy from the sun is going to be 6 times 550 watts. You guys with me? All right. So just keep this as your known information right there. All right. Am I doing this multiplication right? All right. You guys check my numerical calculations. I tend to make mistakes from time to time. All right. But 55 times 6 is supposed to be 33. Yeah. All right. 100. That's good. Okay. So that's the power that you get. Now, you would like to warm up water from 20 to 60. How much energy is required? So say, well, okay, John, no problem. The amount of heat is going to be mc delta T. The mass of the water that you are warming up is coming from a cubic meter of water. What is the mass of 1 cubic meter water, guys? What do you think? Don't need that too many times. So what's the mass of this cubic meter water? 1 kilogram. Okay, very good. All right. You guys agree? I'm just writing it down for now. All right, you have a cubic meter of water. I don't think that's 1 kilogram. That's a big chunk of water, I think. It's like 1 meter long, 1 meter depth. I mean, it's 1 meter deep and 1 meter length. I mean, that's a lot of water. Because 1 kilogram of water is a liter of water. 1 liter bottle, that's a kilogram. Does that make sense? Yes? Okay, all right. So that's not gonna be it. I think this is a little bit too light. Okay, so it turns out a cubic meter of water is 1,000 kilogram, 1 ton. It's not 1 ton noodle or anything, but it's 1,000 kilogram. All right, it's huge. All right, so it's about like a compact car. Right? That's much. All right, so 1 cubic meter is a heavy water. Right? So you have to make sure that every time we talk about like building like a pool or anything, you make sure that your structure can support like a heavy water there. Okay, cool. All right, so that's what it is. So you have a cubic meter of water, and that's 1,000 kilogram. All right, so 1 kilogram, that's actually what's first thing that came into my mind too, like back in the day, like, hey, a cubic meter, but wait. So when we sort of like think carefully, it's just like it's bigger than a kilogram. All right, so that happens to me already in the past. So that's why I kind of like, okay, so I'm being more careful later. All right, so that's what it is. 1,000 kilogram. The C, now you can look it up from this table right here. All right, you can pull the number from here, the water here. So let's say it's about, you can say 4,200 approximately. All right, so roughly that's good enough. All right, or you can be more precise, that's up to you, but approximately there. Okay, so you can do joule per kilogram Celsius, on and on. Okay, so that's your C. The delta T that you have is 40 because you're going from 20 to 60. That is 40. Now, if I just want to be a little bit precise, I would like to add positive sign here. You guys okay with me?
Okay.
What do you think? Okay, the reason I want that because I would like to start sort of like, ease you guys into this. It's a delta. Every time we talk about delta, it has to be final minus initial all the time. All right, we'll have more examples later, but this is, you have to keep in mind that that's every time that you are talking about the change must means final minus initial. So the sign is important because that will give you the direction of that change. Is it the change is a positive direction or negative direction? So over here, that's why I have to do the 60 subtract out with the 20. So that is a positive 40. It's an increase in temperature. All right. So, but for now, because we don't care much about the sign, so that's all right. But at least now we know that is the heat. That is what sort of like is a positive heat. Okay. It has more sort of like a crucial role later. Okay. But now come back to our business here. So now that is the amount of energy that you need to warm up the water by 40 degrees. But then the power is right here. And everyone still remember, yes, I hope the power is just the energy per unit time. The power is just the rate of the energy flow or energy transfer or energy supply, whatever. So the energy that we are talking about right now is just that heat thing that we just calculated up top. All right, so that's it, guys. So from here, you should be able to calculate how long does it take for this solar panel to warm up the water of 1 cubic meter from 20 to 60 degrees Celsius, and you are done. Okay.
Okay.
So any questions so far? So far, so good. So the Q equal to MC equation seems to be sort of like an easy to use equation on and on. So the fun of this business is what's coming next. Here you go. So what we like is this. In reality, sometimes when you supply the energy to any substances, there might be a place where you don't have any temperature change. So sort of remember this a little bit, yeah? And that position or that location of whatever the situation that you are facing at this point, that is the one when you hit phase change or the phase transition. So whenever you're already sitting at the transition temperature, the energy that you supply to the substance won't be used to increase the temperature anymore. But the energy that you supply to the substance will be used to change the phase. All right. What are the phase that you can have? Of course, you can go from solid to liquid if you like. Okay, that is, you can call it the fusion, or you can turn from liquid back to solid. So that is called solidification process. Or the more familiar one, of course, you can do liquid to gas. That's vaporization. You're vaporizing thing. Or the other way around, the vapor can condense down to a liquid. So that's condensation. So as long as you are at that temperature that the transition is happening, the energy that you supply to the object won't be used for temperature change, but it will be used for phase change. That's why we call this the latent heat. Latent is for hidden. Hidden means you won't see any change in temperature, right? There's nothing, no temperature change can be detected there. All right. And this concept is simple, can to put in an equation. It's just saying that the amount of heat during that phase transition is going to be the amount of mass of that substance that get transitions from one phase to the other, multiplied by how much heat per kilogram. So once again, the latent heat is always per kilogram, just like specific heat, right? That's the heat capacity per 1 kilogram. Same thing over here. The latent heat is just the amount of energy that's required to make a phase transition of a 1 kilogram. That's it. So how many kilogram that you can convert or you can do the phase transition, that is M in this equation. And then you're done. Sounds good?
Okay.
All right, so that's sort of another easy to use equation over here. So this table will give you an idea how much you need to do a phase transition. For example, let's focus on water, for example. For water, At 0 degree, everyone knows that's when ice melts, or if waters want to get frozen into an ice, that happens at 0 degree. So phase transition happens right here, and the latent heat of fusion is about that 3.33 times 10 to the fifth. So that means every kilogram of ice will need to get this much energy for that ice to completely melt. You guys with me? 1 kilogram. Or on the other hand, 1 kilogram of liquid water need to release out this much of energy for it to solidify into an ice. Okay, so that's what the latent heat means. Okay, cool.
Okay.
And that's it. By having this latent heat defined, now you sort of understand the whole picture of what happens to a general substance. And then we're going to use water as our sort of like an example. All right, so let's look at this one. This graph is simple. On the horizontal axis, that is the energy added to a water. Let's say you have a fixed amount of water, and then you just keep, transferring energy constantly at a constant rate, at a constant rate to the water. All right, and let's start from super frozen ice. So it's an ice that's deeply frozen at -30. So what happens here? So when you start supplying the energy to this -30 ice, then ice will start to rise in temperature, right? So this portion over here is going to be MC delta T. And the C over here is going to be C of ice. Okay, very good. So far, so good.
Okay.
Now you hit 0 temperature. That is the transition temperature. Now the energy that you supply to the water or to the ice won't be used for energy change anymore. But now more ice will start to melt over time. So there will be more ice melt. So it's going to melting. It's going to keep melting until all of those ice has been melted. Cool. So with that, then now you end with the pure 100% liquid water. So before all the ice completely melt, then you have a mixture between ice and water. Okay. But once all of those ice has melted, then you start to do the rising in temperature one more time down here. Okay. So during this temperature change, then you're looking at another MC delta T. But at the time of the melting, it's just an M times L. Cool. All right. And now if the temperature keep rising until you hit 100 degrees Celsius, then that is the time that you start to do the vaporization. So now you're hitting another phase transition temperature. So the liquid water will start to vaporize more and more, the more that energy you supply to it. So during this period, there will be no temperature change, but more of the liquid water will get vaporized. Okay, so over here, you use another ML again. And of course, it's going to be different L because this is going to be the L for vaporization. But down here, it's going to be the latent heat of fusion. Okay, cool. All right, just different value. All right, so more water get vaporized more and more, of course, until all of the liquid water completely vaporized. Then if you still keep continuing supplying the energy to this, now it's going to be a steam of water now. Then you start growing in temperature again. And that hits another MC delta T. And of course, the C over here will be C of steam now. All right. And C over here will be C of liquid water. So you have to understand that even though they are water, but the water in the ice, like solid ice phase, will have different specific heats than the liquid water. And the steam will also have different value of the specific heat. You guys with me? All right. So that means among these three regions, each region will have different value of the C. All right. Because one is in ice, the other one is liquid water, and the other one is steam water. Cool. All right, guys. So that's pretty much. I have to clap right here. There's nothing much about it. But anyway, okay. So this is what it is. It's just the grand picture of pretty much common substances will follow this trend, right? All the time. You start from solid, you get to the liquid phase, and then you move on to the vapor phase. All right. gas phase. That's what it is. Okay. But of course, there are some exceptions all the time, because you have seen that there are some types of substances at some particular scenario that you can jump from maybe solid to gas, like that we call sublimation, for example, for like a dry ice and stuff like that. All right. So that depends on particular pressure, temperature, and all this stuff. All right. But for a regular setting and everything, once a substance has to go through 3 phases, that's what it is. Okay. And you can actually calculate what is going on. Okay, cool. So far, so good. All right. Now, with that, the fun begins right here. So to make this thing a little bit more useful and the context getting closer to what we are trying to do with the heat and thermodynamics is the topics about the calorimetry. What does this mean? This happens when you have more than one object in thermal contact. Okay, remember the 0th law of thermodynamics? When you have one object, let's say at one temperature, okay, and then you put this in thermal contact with another one with a different value of temperature. So let's say the right side of this one is a colder temperature, so the temperature is low, and the left is, let me call it the hot one, the temperature is high. So you guys know right away when you put them in thermal contact, well, you don't have to put thermal contact. We put them in contact. It will have some thermal effect because you have a hot part and the cold part of your system. So it will have heat flow. And everyone knows it's going to flow from high temperature to low temperature, right? Okay. So I can call this heat Q. But then now, because you have 2 portions of your system, one is losing the energy, and that energy that's losing is flowing into the other side of the system. Does that make sense? All right. So that means the heat that leaves the hot portion, let me call the Q hot, is going to be exactly the same as the heat that entering the cold part. Let me call this the Q cold. They are the same amount of energy. When I say same amount, it means I can write it like this. The magnitude of the energy that gets out from the hot part must be the same thing as the value or the magnitude of the heat that enter the cold part of the system. Sounds good, guys? So I put the absolute sign right here. Okay, just to make sure that, hey, I'm just comparing the magnitude. Why? Because remember, we care about the direction. We care about the direction. So what does it really mean if I want to attach a sign into this? Look at the right side and the left side over here. The heat enter and the other one, heat is coming out. Okay, so heat leaves the system and heat enter the system. So we're going to have some sign agreement right here. If you have an object and you throw in some heat into it, we're going to say that is a positive heat flow. So there is a heat that flow into your system. That is a positive sign. On the other hand, if you take the heat out from your system, that is going to have a negative sign. Okay, you guys with me?
Okay.
Okay, so with that, it means the Q hot must be a negative one because it's the energy that leaving whatever you are considering your system right now. And then the Q cold will have a positive value because the heat is entering your object right now. Does that make sense? All right, so that's why if you want to keep the sign convention alive and you want to use this kind of calorimetry equation, you will have to write it like this. Q hot, the amount of heat that is leaving must be equal to Q cold, but then because you know that the Q cold has a positive sign, I just have to squeeze in the negative sign in front to make them the same. Does that make sense now?
Okay.
Okay. However, in reality, you're probably doing this without knowing it. You're probably doing this. However, to make it correct with the sign convention, you have to do this. But no matter which approach you take, they will end up with the same equation. I will show you with the examples. Okay, sounds good. But at least the calorimetry is kind of easy stuff. It's just saying that, hey, if you have like an isolated system, with me guys, so you have an if you have an isolated system here, when I say isolated, it means there's nothing else that you have to worry about. This thing is isolated from the rest of the universe. So you don't have to worry about the heat leaks out. There's no heat sort of like creeping into this, nothing. It's just only these two sides of your system that you are considering that is exchanging the energy among them. That's it. Okay, so that make it sort of easy to calculate. Okay, and what we are deriving right here, because this one is already isolated, so you can say, hey, everything just has to follow from the conservation of energy. Heat coming out from one must enter the other, because there are no other ways that this energy can flow to. Okay, cool. All right, so with this, let me give you one quick example, and I hope by showing you this, everything will be clear, and then I think we should be good to go. All right, so let's take this one as our final exercise of today's lecture. Sounds good? All right, so this will wrap up what's the concept about the heat, the specific heat, plus the calorimetry, the heat transfer among stuff that's trying to exchange the energy. Okay, you have a 500 gram of ice. So let me sort of draw this one along. Oops, sorry. There you go. So you have 500 gram of ice added to an insulated cup. So that's good. So assume that this cup is insulated. Oh, my cup looks so bad. All right. Okay, let's just draw a little bit nicer there. Okay, here you go. All right, so you have a water in an insulated cup. Okay, just sort of like having fun drawing a little bit here. All right, you have a water here. And now you have 500 gram of ice. Okay, you have this ice waiting for you here. And you want to dump this thing into this. All right, so that's 500 gram. Water right here is 200 gram. All right, and you have an initial temperature of the water to be 50 Celsius. And of course, it's a regular ice, so they're supposed to be at 0 degrees Celsius. No big deal. So the question is simple. What is the final temperature of the whole thing once they mix? Okay, so as you can see, what you are seeing over here is exactly the scenario that we just saw before, right here. So you have only two parts in your consideration right here. One, it's the hot portion of this. The hot portion means that's your water. This is hot, even though this is not, it doesn't have to be super hot, but that's the hot part. And the cold part is ice. So this one is ice. This one is water. Okay, and once you put them in thermal contact, that's exactly when you pour in the ice. They are in thermal contact, and that's it. That will be the heat transfer from hot to cold. Cool. All right, and then one you call the Q hot, the other one you call the Q cold. All right, so let me start from the Q cold, the one that receiving the energy, which is the ice. Eventually, you're going to end up with final temperature because we don't know what the final temperature is yet. So let me call this final temperature to be at X degrees Celsius. So what we are going to do is what happened to the ice, guys? Of course, the ice will receive the energy, Q cold, is going to be equal to first thing first, ice has to melt. Because if you assume that eventually the final temperature of the ice is going to be at X degrees Celsius, first, it's going to have to melt. So that means you're going to have to do ML first. Okay, once this ice has already melted, then you start to creep up in temperature. So followed by the energy that need to raise the temperature all the way to X degrees Celsius. But because when ice has already completely melted, it's going to be water at 0 degrees Celsius, right? So when this ice melts, you're going to be sitting at 0 degrees Celsius, and the delta T that you're going to have here is going to be delta T that go from 0 to X degrees Celsius. Does that make sense? Okay, all right. So now let me substitute the number for you. M, that's a 500 gram. I can turn it into a kilogram by saying that divided by 1,000. So let me write it like 0.5 kilogram. And I can always look it up in the table. What should be the latent heat of fusion over here? I can plug it in there. Next, of course, once it's already completely melted, the mass stay the same. So now you have 0.5 kilogram of liquid water. So you just multiply by the C of just a regular water, look it up in the table again. And now your delta T, what should it be, guys? Of course, is delta. It's going to be final temperature, subtract out the initial temperature. So it's going to be X final minus initial temperature. And that's it. It's done.
Okay.
For the first half. Shouldn't clap just yet.
Okay.
All right. Now, that's, as you can see, whatever you're looking at right now is automatic. See, it's mathematic will take care of the sign by itself. X minus 0, you know it's going to be positive because the final temperature is higher than 0. First term is stay positive all the time, ML. The second term give you another positive. So at the end, this Q core right here will have a net positive number as a result, which make perfect sense because that is signifying that there is a heat flow into the ice. Cool? All right. To make this ice melt and raise the temperature up to X, there must be a heat flow in. Now, let's turn our attention to the other side. Let's look at the Q hot. All right. The Q hot, it seems to be a little bit easier because there's no phase transition involved. So what you have to do is just the M of the water, C of the water, and then the delta T of this liquid water. Let me put the subscript W just to saying that, hey, we are looking at the water side of this whole thing. All right. And the water that's happening over here, the temperature is changing from 50 to X degrees Celsius. You guys with me? Okay, so let's write this one down. The mass of the water is 200 grams, so I can put it as a 0.2 kilogram. Cool. The C of water, let me just keep it there as C of water. It's the same value. Okay. Now, what is the delta T, guys? The delta T is going to be final minus initial. Final is X. The initial is 50. There you go. Done.
Okay.
And you know by your heart that whatever this is going to give you a negative number, right? Because X is going to be smaller than 50. So that's why this is going to be definitely give you a negative value. All right. So I don't know, this one sort of give you something that's related to what you did back in the day of like the high school science or whatever, that maybe when you do the calculation over here, you tend to put the last parenthesis here in the form of 50 minus X. Does that make sense? I don't know. Have you done this before? But it seems like you already know that, hey, the final temperature must be less than 50. So I'm going to take the 50 first and then subtract out the X. So I get a net positive number. All right. But this is the reason why if you do 50 minus X, that means you do the absolute thing already. Because you only take the magnitude, right? You only take the value of the heat, but you don't care about the sign. So it depends on you now. It's your choice. You want to stick with the absolute built in, or you just, hey, I'm just going to have the delta T take care of the sign. And then if you just go like from the first principle and we don't want to deal with the absolute and things. So the final line over here, you have to say Q cold is going to be negative Q hot. And as you can see, once you plug in the negative sign into this equation, then you just flip. Okay, let me write the last portion of this equation. Yeah, see? You already flip the red equation into this 50 minus X, which is exactly what you did back here if you did the calculation by just sort of, care about what is the change and you only pick the positive numbers out of your change. Does that sort of give you, a little bit of clarity between the similarity and the difference between these two equations? Sounds good? All right. So the reason I would like to sort of like explain this in more detail because in the textbook, some textbook prefer this. It's like stick with the sign thing all the time. All right. But some textbooks sort of like, okay, they kind of know that it's more natural to calculate things in purely positive number. So they might add like an absolute sign equation for you along with the regular equation between Q hot and Q cold. Okay, sounds good. All right, but at least this is a good example, and I think this is a standard problems that you should be able to know how to solve, because it's combined the calorimetry, it's combined the concepts of the heat, and plus now we understand a little bit more about the direction of heat, entering positive, leaving negative, and then you can use the equation that explain the specific heat of substance and the change in the temperature if after the heat flow. Yeah, so this is like a sort of like a summary of everything that we are doing right now. Okay, sounds good.
Okay.
Any questions? All right, guys. So if no questions, then that is it for today. Thank you very much.
Okay.
And I will post the video and everything on YouTube. All right, I should be able to set things up everything within this weekend. So the week after this, the upload will be a little quicker. All right, and I have decided to have the video upload for 2 sections separately, because I don't think I talk differently a little bit. It's been a couple of days past. All right, guys, take care. All right, and I'll see you next Thursday. All right, bye-bye.
Okay.